Hello, and welcome to the Academy of Useless Ideas. Today we are going to take a deeper dive into the captivating world of subsequential limits. You may recall that a subsequential limit for a sequence xn is a special point in which all its open balls contain infinitely many elements in the sequence. These points are like bustling hotspots where things happen, and no matter how far you wander from them, there are always infinitely many elements from the sequence nearby. But the question remains, can we always find these mythical points, or are they as elusive as the pot of gold at the end of the rainbow? Let's put on our thinking caps and team up to crack the code of the Bolzano Weierstrass theorem. In the realm of the real line, constructing a sequence without subsequential limits is a piece of cake. For instance, consider the sequence n. Its elements are simply the positive integers. Since each element is spaced apart by a distance of 1, no ball of radius smaller than 1 can contain infinitely many elements, meaning this sequence has no subsequential limits. In fact, many unbounded sequences lack subsequential limits altogether. That's why, for the sake of this discussion, we'll stick to bounded sequences. Speaking of which, can you think of a bounded real value sequence that has no subsequential limits? As you can imagine, testing every possible sequence to determine if it has a subsequential limit is virtually impossible. Therefore, it would be downright amazing if we could prove that every bounded sequence has at least one subsequential limit. But wait, hold on your hats, folks, because that's precisely what the Bolzano Weierstrass theorem states. It asserts that if we restrict the points in the subsequence to be bounded, they must accumulate at some point. It's like trying to corral a group of people in a room. No matter how spacious the room is, they will inevitably find each other. But hold on just a moment. Before we dive into the proof of the Bolzano Weierstrass theorem, let's pause and take a closer look at what makes this theorem so special. You see, the theorem hinges on the idea that the space in question has no holes in it. What do we mean by that, you ask? Well, consider the rational numbers, for instance. You can construct a bounded sequence of rational numbers that would ideally converge to the square root of 2. However, since the square root of 2 is not a rational number, the sequence would not converge, meaning it wouldn't have any subsequential limits. This just goes to show that the Bolzano Weierstrass theorem would fail in any space that has holes in it. This observation underscores the importance of the supremum property in proving the Bolzano Weierstrass theorem. Specifically, the proof relies on the nested interval property, which is a consequence of the supremum property. To apply this proof strategy to an arbitrary bounded sequence, we need to find a chain of bounded, closed, nested intervals and show that an element in their intersection is a subsequential limit of the sequence. To start, let's pick m as a bound for the sequence and choose a0 equal to -m and b0 equal to m, so that all the infinitely many values of the sequence fall inside the closed interval between a0 and b0. Now assume that an and bn have been chosen such that infinitely many values of the sequence lie between an and bn. We can then calculate Cn as the midpoint between an and bn. If the interval from an to Cn contains infinitely many elements of the sequence, we choose an plus 1 equal to an and bn plus 1 equal to Cn. Otherwise, the interval between Cn and bn must contain infinitely many elements of the sequence, and we can pick an plus 1 equal to Cn and bn plus 1 equal to bn. The intervals constructed in this way are bounded, closed, and nested. Therefore, their intersection is non-empty. Let's call an element in the intersection x sharp. We claim that x sharp is a subsequential limit of the sequence. To prove this claim, note that since the construction is based on a bisection, the length of the nth interval is 2 to the power of 1 minus n times m, which tends to 0 as n goes to infinity. This means that for any arbitrary epsilon greater than 0, we can choose a capital N such that the length of the nth interval is smaller than epsilon. But then the ball of radius epsilon around any point in the interval completely contains the interval. We also know that the interval contains infinitely many points of the sequence. Since epsilon was arbitrary, this shows that every ball around x sharp contains infinitely many elements of the sequence, and therefore x sharp is a subsequential limit. The inquisitive mind of a mathematician might wonder whether the Bolzano Weierstrass theorem holds in any metric space. As we noted earlier, the theorem fails to hold in spaces with holes. However, so far we have only defined holes for ordered sets. In order to get a more general version of Bolzano Weierstrass, first we need to define holes in metric spaces. Moreover, our proof relied on the bisection method, which doesn't work in arbitrary spaces. Therefore, a more precise version of boundedness is needed to generalize the theorem. However, these concerns are left for future explorations. For now, we can be confident that in the real numbers, every bounded sequence has a convergent subsequence.